task to track a single pill. Problem statement.
Problems with pill intake. More than half of patients don't take their medication correctly, which leads to missed doses, double dosing, and serious health risk. Traditional pill organizers can't confirm if a pill was actually taken. This problem costs the U.S. hundreds of billions of dollars each year, especially affecting older adults. Caregivers also struggle because they don't always have real-time visibility into daily medication use. Potential markets. Our system fits into several key markets. It supports individuals managing chronic conditions and older adults who need daily reminders. It also benefits caregivers, assisted living facilities, and home care agencies through verified tracking. In telemedicine, it allows providers to access adherence data remotely. Pharmacies can use smart blister cards to improve safety, and the global pill dispenser market continues to grow rapidly. Solution. Our solution is a sensor-enabled smart blister card that tracks real pill removal. It helps prevent missed doses, double dosing, and lack of caregiver visibility. By using IoT sensors and a microcontroller, the system automatically confirms when medication is taken. This allows for real-time tracking at home, lowers healthcare costs, and gives both patients and caregivers peace of mind.
Mechanical design overview. We performed a linear static FEA in SOLIDWORKS on the tray deck rail subsystem shown by the golden arrow, which is integrated with the enclosure. The model included two primary loads, gravity and a pressure load representing a fully loaded blister card. The rail ends were constrained at the connections to the enclosure, and roller supports were applied along the bottom surface of the box to represent how the device rests on a flat surface. Because our main concern was tray sagging, we used URES as the governing metric. The maximum deflection was only 8.63 times 10 to the negative 3 millimeters, confirming the rails are mechanically robust under expected use. For thermal performance, we modeled the PLA enclosure using natural convection with a heat transfer coefficient of 5 watts per meter squared Kelvin. Based on worst-case converter efficiencies, the internal electronics dissipated a total of 2.04 watts. Using a steady-state energy balance, this results in a temperature rise of about 3.6 degrees, putting the internal temperature near 28.6 degrees Celsius. This is well below PLA's material limits, indicating the enclosure will maintain its mechanical and dimensional integrity during operation.
So we will now go over the electrical design overview, including schematic design, PCB layout, and how all of these choices fit into our overall prototype. Starting from the left, you're seeing the processing board. We designed it so that every board in the system has clean access to the Phoenix connectors, which pass all the digital signals across the entire device. On this board, we have the Raspberry Pi Zero, a 32-channel multiplexer, another 4-channel multiplexer, and the pill tracking digital inputs. We also have additional Phoenix connectors for the user interface peripherals. These peripherals include the fingerprint sensor for security, the LCD for accessibility and feedback, the solenoid for our locking mechanism, and some general purpose input and outputs for controlling and lighting inside the device. Because every pill cavity sends a digital detection signal, we have 12 pills per board across 3 boards, so this processing board routes a total of 36 wires dedicated for pill tracking. The middle image shows our pill detecting boards. Each of these boards contain a repeated sensor design, a photoresistor for each cavity, and a Phoenix connector that outputs the detection logic to the processing board. The idea is simple. When a pill is removed, more light passes through the clear cavity of the blister card. This photoresistor picks that up and the signal gets processed by the onboard logic, and then that state is sent to the processing board for logging. We built these boards as identical modules so they could scale easily. 12 cavities each, mechanically aligned, and electronically isolated for clean signal routing. Finally, on the right is our power board, along with the interior light plane. The power board takes a 3.7 volt lithium-ion battery and uses a rechargeable boost module to step it up to 5 volts. That 5 volt powers the RGB LEDs, the white interior LED strip wrapped around the perimeter of the device, and anything else that needs a higher current source. We also generate 3.3 volts on the same board to run all the sensor logic safely and consistently. The rechargeable power board or rather module, extends battery life and makes the device portable while still supporting USB charging, so the user never has to remove the battery. This slide shows the 3 PCBs we designed. The sensing board on the top left contains the 12 photoresistor voltage divider circuits, with each output routed to the top Phoenix connector for the MUX. The power board on the bottom left handles the battery input, boost module, and 3.3 volt buck converter to distribute stable 5 volt, 3.3, and ground across all boards. And on the right is a processing PCB, which integrates the Raspberry Pi, both MUXes, and the I2C expander, as well as the peripheral connectors, with routing optimized to keep the signal path short and every GPIO easily accessible.
Firmware and application overview.
This slide illustrates the overall software logic running on the microcontroller. The system begins with the initialization phase, powers on, loads the medication schedule set from the Flask app, and activates the sensors, LEDs, and motors. The main operating loop continuously checks if it's time for a pill based on the stored schedule, and if it is, the correct slot is unlocked, the LED turns on, and a photoresistor detects whether the pill is actually taken. On the right, the system also listens for any updates from the Flask app, such as schedule changes or dosage adjustments, and applies them in real time. At the end of the day, the device enters a nightly mode where it confirms whether all meds were taken and then goes into a low-power sleep mode. Overall, this diagram shows the software, hardware, and user data working together to automate and monitor medication adherence. Slide shows a web interface that controls our medication dispenser system. The login page ensures only authorized users like patients or caregivers can manage the medication schedules. On the right, we have the medication schedule page. Here, users can enter the pill name and specific times it should be taken. Once this information is submitted, it determines the exact unlock schedule for the blister card slots on the physical dispenser, meaning the software directly drives the hardware timing. So essentially, what the user inputs here becomes a real-time schedule that the Raspberry Pi follows to unlock the correct pill slot at the right time.
Thank you.